Alright, good morning again. This time we're going to be working back with our trig functions that we learned yesterday in lecture 3. And this time just applying it to more scenarios. This time we're not going to be just working with right triangles, but we are going to be using right triangles to kind of guide us through this topic. We are actually going to be working with trig functions within unit circles. So a unit circle is just we came up with this term to describe this scenario. So we have a circle that's centered at 0, 0, and the radius is 1. So r is equal to 1, and center is equal to 0, 0. If you have this scenario, you have a unit circle. Units are just when you have one thing of one unit. So what does that mean for trig? What that means is if we have a triangle that sits on, in this scenario, one vertex is on 0, 0, another would be on the circle, you're going to get right triangles, or the possibility to put a right triangle in there, and it makes things simpler. It, in fact, makes it so that the hypotenuse, let's say that this is our triangle, makes it so our hypotenuse is our radius, and our radius is 1. So when you get to this point, sine and cosine, you don't have to worry about a second relationship with it, because the hypotenuse is always 1. So it's just pure x and y for your cosine and sine in that order. Hard part for me to remember is just that x is usually the first thing, sine is usually the first thing. They don't go together. So x goes with cosine, y goes with sine. But because of that, tangent is going to be y over x, opposite, since this is y, this is x, opposite over adjacent, y over x. And this has been a way that you have described slope. So tangent, as long as the coordinate is going through, or as long as this line is going through 0, 0, and it goes through this point, y over x is going to be a slope. So tangent is often described as the slope of a point as well because of that. It is the slope of the hypotenuse, but you don't have to remember this. This is just some other applications of it. And then as long as you can remember those, yesterday we talked about cosecant, secant, cotangent. These are just reciprocals of those three. So with the hypotenuse being 1, in both of those you'll have 1 over y, 1 over x. Cotangent is the inverse of y over x, or just x over y. So going to number 1, let's get rid of this. Number 1 has a coordinate -1/2 root 3 over 2. And I'm just going to go ahead and jump into the triangle. Now -1/2 and root 3 over 2 is the coordinate, but you can also label the side lengths. And even though it's a triangle, I'm going to put -1/2 here. It kind of just helps picture it, but this is where it gets different than regular right triangle trig. We do have our right angle here. Our hypotenuse is 1, so we're kind of just working with this made up triangle. But finding sine of t, where t is this angle, cosine of t, tan of t, cosecant t, secant t, cotan t. I am sine of t is the y value, so root 3 over 2 or root 3 over 2 over 1, but cut to the chase. Cosine t would be the x value, -1/2. Tangent is the slope of this line, or x over y, or sorry, y over x. Y is root 3 over 2. I'm going to write it like this. I'll show you a second on y. -1/2 is your x value. These 1/2s are going to, or the halves are going to cancel. So this is root 3 over negative 1 or negative root 3. If you flipped and multiplied the negative 1/2, you could also get to this point. But negative root 3 should be tan of t, which should be the slope of that hypotenuse again. Flipping sine over t, or 1 over this, you should get 2 over root 3. Rationalizing the denominator, you should have 2 root 3 over 3. Secant is, again, flipping this fraction or doing 1 over this fraction. 1 divided by negative 1/2 is negative 2. And then when we get to flipping fractions like this, I tend to flip the unsimplified version. That way I don't have to work with root 3 if I don't have to. In this case, it doesn't matter which one you do. You get negative 1 over root 3. Rationalizing that, it's negative root 3 over 3. If you need help rationalizing, or if you need help with the idea of flipping the fraction, again, stop by office hours. We can talk more about it. But I'm going to try to keep these short and sweet if I can. Alright, quadrantal angle. Quadrantal is just a fancy way of saying that the angle ends on one of the axes. So it starts here always, but it might end here, it might end here, 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 or here. When you have quadrantal angles, the 6 trig functions will either be 0, 1, negative 1, or undefined. Those are the only 4 things it could be. You do have to remember what you're working with, though, and what to look for. As a reminder, tan of theta is y over x, or the slope, think of that. That kind of helps with the undefined portion. Cotangent of theta is x over y. And then the other ones are there as well. But these are the ones that are most commonly going to be undefined. So just keep a heads up on that. 0 is right here. So 0 degrees is ending where it starts. So this coordinate that it ends on is 1, 0. Sine is the y value. Sorry, sine of theta is the y value. Cosine of theta is the x value. Tangent is the slope, or y over x. 0 over 1 is 0. Cosecant of theta is flipping this fraction, so 1 over 0. I can't divide by 0. This is undefined. Cosine of theta, if I do 1 over 1, or sorry, secant of theta, if I do 1 over 1, I get 1 again. And cotangent is going to be 1 over 0, same issue as sine, or cosecant. It's going to be undefined. Next, pi over 2, working with radians. If I go pi over 2, that's half of pi. Pi is half a revolution, so we're ending right here. Think about this angle here. And if we're working with that angle, we have 0, 1 as that coordinate that lands. Thinking about 0, 1 when we go through our 6 trig functions, cosecant, theta, secant, struggling, okay. Cosine theta, secant theta, tan, cotan. Alright, sine is the y value, 1. Cosecant is flipping that fraction, which is still 1. Cosine, 0. Flipping 0, so 1 over 0 is going to be undefined. Tangent is going to be that slope. So this slope is a vertical, this line is vertical. Vertical lines have an undefined slope. Also, we're dealing with 1 divided by 0. Undefined. And then cotangent, we are doing x over y. So 0 divided by 1, 0. Okay, again, your 4 choices when you're dealing with a quadrantal angle. If I'm asking you for a trig function, it's going to be one of these 4 things: 0, 1, negative 1, or undefined. So far we haven't seen -1, but it can still happen. Finding the exact value without a calculator. Cosine of 7 pi. We want to find the x value. And then for cotangent, we're going to find x over y. So we need to know those values. For cosine, if we're working with the unit circle, I'm going to do a spiral. Even though it's a spiral, just think about that as it's on the unit circle. That way you can actually see how many revolutions we're doing though. This is pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi. So if I was on the unit circle with these spirals, this would be -1, 0. Cosine 7 pi is the x value, or -1. 7 pi over 2. Pi over 2 is our 90-degree angle, so basically I'm just going to hit 7 of these axes. So 1, 2, 3, 4, 5, 6, 7. If I was staying on the unit circle, this would be 0, -1. X over y is 0 over -1, which is equal to 0. And you're done. Quadrantal angles are really quick, or at least they're nice, neat numbers. Again, you have 4 choices: 0, 1, -1, or undefined. All right, if you are someone in the college or wanting to take the college course, please go through this proof on your own, see if you can do it, and then pause this and then go through the proof with me, see if there's any point that makes sense or doesn't make sense. Come to office hours for questions, as per usual. So it says prove that a 30, 60, 90 triangle, that the length of the hypotenuse is twice the length of the shorter leg, and the longer leg is √3 times the length of the shorter leg. To do this, you want to imagine an equilateral triangle, where with equilateral triangles, if you remember, it's also an equiangular triangle, where all angles are 60 degrees, all side lengths are the same. And so I'm going to try to prove that a 30, 60, 90 has these properties. Using this idea of an equilateral triangle, I can bisect the angle, bisect the side over here as well, and I get a 30, 60, 90. In fact, I get 2 of them. So this is a 60, 30, 60, 90, 30, 60, 90. I'm going to expand one of those triangles. The base of this triangle is half, or the base of this triangle is half of this, so half of x, 1/2 x. The hypotenuse of this triangle is still one of the sides of the equilateral. So now I have the first part proven, essentially. So the hypotenuse is twice the length of the shorter side. If I multiplied this by 2, I'd get x. So the first part's done. If I was writing this out for a true proof, I wouldn't necessarily be done, but that's pretty much the point, is that if I double this side, I get that. The next portion is proving that this is √3 times greater than this, which would be √3 over 2x. So we're going to try to get to that point. To do this, we're going to use the Pythagorean theorem. Hypotenuse is equal to a squared plus b squared. And we're going to, again, try to prove that this is √3 over 2 times x. If I actually square 1/2 x, I get 1/4 of x, where x is just being squared. Alright, 1x squared minus 1/4 x squared would be 3/4 x squared. And I'm going to take the square root of both sides. X and b are no longer squared. The square root of 3/4, I'm going to take the square root of 3. The square root of 4 is 2. So I can then plug that in here. And what I have, if I were to multiply this by root 3, I have root 3 over 2. So here is the second portion of the problem proven. So I would be done. You're good to go from here. Now it says to use this fact to find these values. So I'm going to draw a 30, 60, 90. And I'm going to use the unit circle. So 1 opposite to this, this is half of the hypotenuse, or 1/2, and this should be root 3 times the shorter side. So working with this triangle, I can quickly find these values. So think about this as y, think about this as x. So root 3 over 2, cosine is x, tangent is going to be root 3 over 2, I'm going to write it down here, root 3 over 2 divided by 1/2. Flip and multiply, this is root 3 over 2 times 2 over 1, or just root 3. Flipping the fraction of sine, we're going to get 2 over root 3. If you rationalize the denominator, it's 2 root 3 over 3. Again, if you're having trouble with this concept, please stop by office hours and ask questions. Secant is 1/2 flipped, which is just 2 over 1, or 2. Cotangent is tangent flipped, so that's 1 over root 3. If you multiply by root 3 over root 3, you're going to get root 3 over 3. Okay. Sine, cosine, all of that of 30 degrees is taking it from this angle, or you can draw a new triangle working with that 30. And now 1/2 root 3 over 2, 1. Now we're working with a different x and y. This is y, this is x, but the sides are all the same, they're just kind of swapped around. So if you're thinking about this triangle, you could do the same thing between the two. Cosine and sine, cosine of 60, sine of 30, are the same thing, because now the opposite is the adjacent, and the adjacent is now the opposite. Cosine of 30 is sine of 60, root 3 over 2. Tangent is still y over x, but now our y's and x's have switched. So this is 1/2 over root 3 over 2, but we just did that calculation over here. So cotan of 60 is the same thing as tangent of 30. So root 3 over 3. If you need to see that, you could calculate cotan of 60, or tangent of 30. You'll see that you're using the same numbers in the same place. Cosecant of 30 is going to be sine flipped, or secant of 60. And then secant of 30 is cosine flipped, or cosecant of 60. So 2 root 3 over 3. Cotan of 30 is the same thing as tan of 60. Again, you're just using the same numbers, just moved around a little bit. So whenever you're working with the 6 trig functions of 2 different angles within the same triangle, you're going to see a lot of the same numbers, just moved around. Alright, same idea. This time we have a 45, 45, 90 triangle. And we want to prove that the hypotenuse is root 2. Basically, we want to prove this. So it's root 2 times the length of the leg. To do this, okay, again, stop what you're, if you're wanting to prove this on your own, stop what you're doing or stop the video and prove it on your own. Check in with me if you need help or if you want to check your work. But if you just want to watch, this is what I want to prove, so I can't use this yet. So I'm going to ignore that, but I'm trying to get there. Let's imagine I have a square, 90 degrees, all the same length. that length is x. Now if I have a 90-degree angles everywhere and I bisect those two angles, now I have a 45-degree angle on both of these. Okay. And I guess you don't really need to use that, but if you go back into this idea, now we know we have 45. I guess that's where it comes from. But 45, 45, 90, x in x. Pythagorean theorem, again, you're going to go x squared plus x squared equals hypotenuse squared. We have two x squares here. So 2x squares equals c squared. You're going to take the square root of both sides. Square root of x squared is just x, and the square root of 2. All right, we got that the diagonal or the hypotenuse is root 2 times greater than this. So we're done. We got it. Using this idea, we're going to come up with sine, cosine, tangent, all of that of 45 degrees. 45 degrees. And again, I'm going to use this as, or I'm going to use that 1 as our hypotenuse. Imagine that we're using that unit circle. If this is root 2 times this, that means that this is 1 divided by root 2. Okay, same as this. But you're not going to see 1 over root 2 very often. 1 over root 2, if I rationalize the denominator, is root 2 over root 2. Root 2 over 2 after I multiply it out. So root 2 and 2, same thing with this one, root 2 over 2. And since I'm using a unit circle, these are my x and y values. Okay, this is my y, this is my x, this is root 2 over 2, root 2 over 2, and then if I flip the fraction, this is a case where I want to use the unsimplified version. So 1 over root 2, if I flip that, it's just root 2. And this is just root 2. Or you could think about this as 2 divided by root 2, which is root 2 squared divided by root 2. Those cancel. So I'm just left with root 2. This is probably the hardest part to get used to, just because it's a quick, or it turns into something quick. Eventually this becomes second nature, so just stick with it. Again, stop by office hours if you're having trouble with it. Tan of 45 is y over x. Y is root 2 over 2, x is root 2 over 2. Root 2 over 2 divided by root 2 over 2. Well, that's the same thing over the same thing, so that's just 1. If I flip the fraction, I have the same thing. So the cotangent of 45 is also 1. All right. So tomorrow we'll be doing the same unit. Well, we'll be working with unit circles. Unit circles is a huge portion of this class, so I want to make sure that we have it down. And this is just using those most common angles in this course. But we'll move into other scenarios tomorrow. Stay tuned. Again, stick to 30 minutes if you're doing the high school credit. Do all of the MyOpenMath homework if you are doing college now. And I will see you tomorrow.